So, but first, again, we have here the forcing function dependent on that. And again, this is a vector. Then we got here our transposed bias functions, and here our weights. And again, this is a vector, the weights are the vector, and this will be a matrix. And now I would simply rewrite in some kind of easier form. Okay, again, I will write this here as epsilon. So this will be now a more general form. This epsilon are our measurements. No, come on. So this epsilon will be our, this y, not epsilon, sorry, this y will be our measurements. Or measurements will be, or will hold our measurements. And then we have here a x, and this is a matrix. And this is our system matrix. And our system matrix consists, in our case, of our radial basis functions, system matrix. And then we have a parameter vector, and we call that here better. And if our parameters, or if we could find any parameters which fit together with the system matrix perfectly or the measurements, this would be really equal. But since this will be not the case, since our measurements may be disturbed or our parameter vectors are not perfectly fitting, so we have to add an error term, and this we call simply epsilon, and this is also a vector. So, and what we want to do right now is to find out which parameters better, or in our case, which weights W are fitting best the measurements. And in order to do so, to find out these parameters, we have to minimize our error epsilon. And we will not even minimize the error epsilon, only we will minimize the squared error. So we will minimize the squared error epsilon transposed multiplied by epsilon. Okay. And in order to do so, we can now write the following. We have here the epsilon multiplied by epsilon is equal to y minus x better transposed multiplied by y minus x better. And we can write that out. This is y multiplied by y minus 2 multiplied by beta transposed multiplied by x transposed epsilon plus beta transposed x better. So, and the aim is to again minimize this term. So, and in order to find really the minimum of this term, we have to simply take the derivative with respect to the parameters better. So we simply can write the derivative, or define the derivative in regard to the parameter vector better, and got then minus 2x transposed multiplied by y plus 2x transposed x multiplied by better, and the minimum will be where the derivative of the error function is equal to 0. So, and since we want to know the parameters where we have the minimum of our error function, so we want to know the parameters better here, we have to rearrange it. We have to rearrange this equation to the following form that we have better on simply just one side. So we got then 2 multiplied by x transpose x better is equal to 2x transposed y, and on the last step we get then better is equal to x transposed x, and then the inverse multiplied by x transposed and our measurements epsilon. And this is our equation which we require in order to estimate our parameters better, or in our case our weights w. So if we write this now for our case, we got the following. We can calculate our parameters w, or weighting parameters w, as the following: psi transposed psi plus sigma, and this is the identity matrix, and then the inverse multiplied psi transposed, and then the forcing function. The measurement values, I called that ft, right? And this ft again you can simply get by measurements from ft is simply x dot dot t minus tau squared alpha better g minus xt minus x dot t through tau. Okay, so, and with this formula we get then the weights, and then we have our parameterized trajectory linear completed, and can then use these weights and our given forcing function, which is dependent on the radial basis functions, in order to then estimate a desired trajectory x dot dot, and so on and so forth. And then we get not only x dot dot, we can then also get x dot and x by using simply using simply solver for differential equations. Okay, this is nearly the end of our task 1 of the second exercise of the Humanoid Robotics course. I want to simply point out some facts of or some advantages and disadvantages of the trajectory generator based on this simple spring damper model. Okay, again I will simply write that here down. Our model, it's alpha better g minus x dot plus a forcing function, and one advantage would be that this model, or the behavior of this model, is well defined. Because it's a realistic model from the nature, and it has stability. So this model will be stable different will be stable by construction. Why is that? So because we have used, remember, we have used a spring and a damper. And the damper in our model will make sure that we always get back to our equilibrium, so that not getting increase the system. So this is the reason why it's stable by construction. But the disadvantage of this model is that you can only represent a limited class of possible movements. So you can't really represent every movement you can imagine with such a model. But therefore you got the stable behavior and a well-defined behavior. Okay, this was the first task of our second exercise in humanoid robotics, and it was about dynamical system. And the next task, so task 2, is then about probabilistic systems.